The chip in an AI server puts out about as much heat per square centimeter as a fuel rod in a nuclear reactor. We have learned to pull that heat out. Water does it, and it does it well. Then the water comes out of the rack warm, not hot, warm. That is the whole problem, and it is not an engineering mistake. Start with the number on the box. Every processor has a rated power, the electricity it draws, and therefore the heat it makes. In 2020, a data center accelerator was rated at 400 watts. 2 years later, 700. By 2024, 1,000. The part shipping this year is rated at up to 2,300 watts. One component, 6 times the draw of the part from 6 years ago. And the modern accelerator is not one piece of silicon. The 1,000-watt part is 2 dies, side by side, each around 800 square millimeters. Why 2? A lithography machine prints a rectangle of only about 858 square millimeters in one shot, the reticle limit. So the industry stitches 2 dies together. Now the arithmetic that matters. 1,000 watts of heat coming off roughly 16 square centimeters of silicon. That is about 62 watts leaving every square centimeter. Hold that number. Inside a pressurized water reactor, a fuel rod surface gives off about 60 watts per square centimeter on average. At the hot spots, closer to 150. So the comparison is fair. Per square centimeter, an AI die moves heat at reactor-core intensity. The difference is everything around it. A reactor is built from the ground up around that heat. The chip is a part you slide into a rack. Now stack the parts. A Hopper-era rack drew around 40 kilowatts. The Blackwell generation moved that to 120, 130. The rack shipping later this year sits between 190 and 230 kilowatts. The generation after it is planned at around 600 kilowatts in one cabinet, the width of a wardrobe. At that point, a fan is not a weak solution. It is not a solution. Air carries very little heat for its volume. Moving a rack's worth takes enormous flow, and the faster you push it, the more the fans eat. The industry did not switch to liquid because liquid is fashionable. It switched because the next generation has no air-cooled version at all. No air variant at any power level. The compute trays and the switch trays ship without fans in them. Air did not get worse. The chips walked off the end of what air can do. So, water. And here the story turns pleasant for a while, because water is very good at this. A cold plate sits directly on the die. Coolant runs through fine channels inside it, picks up the heat, and carries it out in a closed loop. Closed loop matters. The same fluid goes round and round, a working fluid, not a supply. It carries heat, nothing else. And it is dense. It moves enormous heat through a pipe the width of your wrist, with a pump instead of a wall of fans. But the real prize is not the pipe. It is what the pipe lets you stop building. There is a standard for this, and it is refreshingly blunt. Facility water classes W17, W27, W32, W40, W45, and W+. The number is the highest temperature of water you may send in. W32 means the equipment runs on water supplied at 32 degrees. That sounds minor. It is the whole economics of the building. If your chips demand cold water, you must manufacture cold, with chillers, machines that eat power all year. If your chips accept warm water, you can often skip that and cool the loop against outside air. And above roughly 32 degrees of supply, in most of the world's geographies, a chiller is not needed at all. The hotter the machines tolerate their coolant, the less machinery you buy, power and maintain. Liquid cooling deleted a whole category of equipment. And it did something else, almost by accident. It gathered the heat. In an air-cooled hall, it is smeared across a room and blown outside. In a liquid loop, it travels in a pipe. Which raises the obvious question. If it is all in one pipe now, why is that heat not warming something? A greenhouse, a pool, a town. This is where the story stops being pleasant. Start with the older kind of site, so the ladder is clear. In Odense, Denmark, a large air-cooled data center gives its heat to the city. Air-cooled means the heat is picked up from warm air by water coils. It comes off at about 27 degrees. 27 degrees is barely above body temperature. You cannot heat a radiator with it or run a process with it. Now bring back the liquid loop, because it genuinely helps. Water leaving a cold plate is warmer than any air-cooled hall manages. Warm, not hot, but warmer, cleaner in one place, moving at a known rate. For reuse, a real improvement. And it is still not enough. Because of what a heat network requires at the other end. Modern district heating, the fourth generation kind, wants water at 60 to 70 degrees. The older networks, which is what most European cities actually have in the ground, want 70 to 100. So there is a gap between what leaves a data center and what a city will accept. Temperature gaps do not close by wishing. In Odense, they close it with hardware. Next to the site sits a station of large ammonia heat pumps. A heat pump takes low temperature heat and pushes it higher by spending electricity. That plant lifts it to 70, 75 degrees, what the network will take. It works. It is not free. On that lift, you get between 2.5 and 6 units of heat per unit of electricity spent. Look at what got built here. An industrial plant, ammonia compressors and all, whose only job is turning warm into hot. And that is the answer the episode has been circling. Heat has two properties, not one. How much of it there is, watts, and what temperature it sits at. The first is enormous and grows every generation. The second barely moves. A data center makes a gigantic quantity of very low-grade heat. And low-grade heat is stubborn. The second law is precise. Heat moves from hot to cold on its own, and never the other way without work. Every degree you add costs electricity, the exact resource the building was trying not to waste. So the industry moved the right way and still came up short. Not because the engineering is bad, but because physics sets the ceiling. Which brings the last, quietest fact. Heat reuse is not an unsolved technology. It is well understood, and it is rarely done. Analysts who track the industry count around 60 documented projects in Northern Europe, the world leader at this. Germany legislated it. from July, new data centers there must reuse 10% of their energy, 20% by 2028. A rule exists because it does not happen on its own. So the heat goes out, gigawatts of it, at the temperature of a warm bath, into the air above the most expensive silicon ever made. Not because nobody thought of it, because the second law charges rent, and in most places nobody wants to pay it. Next time, the other thing these buildings do at scale, move data. And what happens when everyone arrives at once? Rush hour on the wire.